Welcome to this problem-solving session. Today, we'll explore LeetCode problem number 1614, maximum nesting depth of the parentheses. In this problem, we aim to determine the maximum depth of nested parentheses in a valid parentheses string. Stick around as we break down the solution and key concepts step by step. In this problem, we are tasked with analyzing a valid parentheses string, denoted as S. This string consists exclusively of the characters, and a string is considered valid if it adheres to one of three conditions. It is either an empty string, it can be represented as a concatenation of two valid parentheses strings, or it can be represented as an open parenthesis followed by a valid parentheses string and then a closing parenthesis. The main objective is to determine the nesting depth of the string, which is defined as the maximum number of open parentheses that are nested within each other. For instance, the string has a maximum nesting depth of 3, as the parentheses are nested 3 levels deep, while the string has a depth of only 1 since no parentheses are nested inside others. Ultimately, the goal is to return the maximum nesting depth for the input string S. The solution to this problem involves returning an integer that represents the maximum nesting depth of parentheses in the string S. Let's go over some examples to clarify this concept. For the input S equals 1 plus 2 by 3 plus 8/4 plus 1, the output is 3. This is because the deepest level of nesting occurs in the substring 8/4, where the parentheses are nested 3 layers deep. Similarly, for the input S equals 1 plus 2 plus 3, the output is also 3, as the maximum depth is demonstrated by the substring 3, where the parentheses reach a depth of 3. Another example is the input S equals 1 plus 2*3 /2 to 1. Here, the output is 1 because there are no nested parentheses. Every pair of parentheses is independent, resulting in a maximum depth of 1. On the other hand, for the input S equals 1, the output is 0 because there are no parentheses at all in the string. Without any parentheses, the nesting depth is simply 0. The problem also specifies some constraints and edge cases we need to consider. For instance, the length of the input string S can range from 1 to 10,000 characters, and S will always be a valid parentheses string. Valid strings can include digits and operators such as plus, dash, asterisk, and /, interspersed with parentheses. In edge cases like 123 plus 456, where there are no parentheses, the result should be 0. For strings like 1, which contain a single pair of parentheses, the depth is 1. Deeply nested strings, such as 1, must be correctly handled even when the depth is very high. Finally, for strings containing a mix of numbers, operators, and parentheses, such as 1 plus 2 by 3 plus 8/4 plus 1, the solution must accurately track and compute the depth. This involves analyzing how parentheses open and close throughout the string, ensuring that the maximum depth is calculated even in cases where nesting levels vary. By addressing these constraints and edge cases, we can ensure that our approach works efficiently for all valid inputs. To solve problem number 1614, we need to determine the maximum depth of nested parentheses in a given string. Let's begin by considering some possible approaches. The first is the brute force approach. The idea here is straightforward: traverse the string one character at a time while maintaining a counter to track the depth of open parentheses. Each time we encounter an opening parenthesis, we increment the counter, and for each closing parenthesis, we decrement it. As we iterate, we keep track of the maximum value of the counter, which represents the maximum nesting depth. This approach is efficient because it only requires a single pass through the string, giving it a time complexity of O(n), where n is the length of the string. Additionally, it doesn't require extra memory beyond a few variables, making its space complexity O(1). However, its simplicity comes with the trade-off that we must carefully manage the counter to ensure correctness. Another approach involves using a stack. Here, we simulate the nesting process by pushing an opening parenthesis onto the stack and popping it for each closing parenthesis. The maximum depth corresponds to the largest size the stack reaches during traversal. While this approach is similarly efficient in terms of time complexity at O(n), its space complexity is higher O(n), because the stack can grow as large as the length of the string in the worst case, such as when all characters are opening parentheses. While the stack-based approach offers an intuitive way of handling nested structures, it requires additional memory, making it less space efficient compared to the counter-based method. Another approach we could consider is a recursive solution. In this method, we recursively calculate the depth of the parentheses by identifying subproblems within the nesting. However, this is less practical for this problem, as recursion introduces unnecessary overhead. The time complexity remains O(n), because we still need to traverse the string, but the space complexity becomes O(n) due to the recursion stack. This makes it less efficient, especially for a problem that can be solved with simpler methods. Additionally, implementing recursion for such a straightforward task can make the solution more complicated than it needs to be. Thus, while recursion could theoretically work, it's not a favorable choice here. Given these considerations, we select the brute force approach using a counter as our chosen strategy. This method is ideal for this problem because it allows us to solve it with a single traversal of the string, incrementing the counter for each opening parenthesis and decrementing it for each closing one. Whenever the counter increases, we update the maximum depth. This approach leverages the key observation that the depth corresponds to the number of open parentheses at any given time. Importantly, we don't need to store the parentheses themselves, which eliminates the need for a stack. The simplicity of this approach ensures that it is both time efficient, with a complexity of O(n), and space efficient, with a constant space complexity of O(1). While the stack-based approach might seem conceptually easier for some, it introduces unnecessary space overhead. Similarly, the recursive approach is harder to implement and less practical, making the counter method the clear winner. This strategy balances efficiency, simplicity, and resource usage, which is why it's the optimal choice for this problem. In conclusion, the counter-based approach stands out as the most efficient and straightforward method for solving this problem. It achieves an optimal balance of simplicity, performance, and minimal resource usage. By avoiding the overhead of additional data structures or recursion, this method provides a clean and effective solution. With a linear time complexity of O(n) and a constant space complexity of O(1), it's clear that this strategy is the best fit for the task at hand. By focusing on the essentials, such as maintaining a counter to track depth, this approach ensures correctness while keeping the implementation as simple as possible. In this problem, we need to determine the maximum nesting depth of parentheses in a given string S. The nesting depth represents how deeply parentheses are nested within one another. For example, in the string S equals 1 plus 2 by 3 plus 8/4 plus 1, the deepest nesting occurs within 8/4, which has a depth of 3. Our task is to identify this maximum depth. To solve this efficiently, we use a single pass approach. First, we initialize two key variables. The current_depth variable keeps track of the depth of open parentheses as we traverse the string, while the max_depth variable tracks the deepest level of nesting encountered so far. Both are set to 0 at the start. With this setup, we can dynamically calculate the maximum depth as we process each character in the string. Now, to find the maximum nesting depth, we traverse the string character by character. Using a for loop, we inspect each character in S and perform specific actions based on its type. If the character is an opening parenthesis, we increment the current_depth by 1, since we are entering a new level of nesting. At this point, we also update max_depth to ensure it reflects the highest depth encountered so far. If the character is a closing parenthesis, we decrement current_depth by 1, as we are exiting a level of nesting. This operation is safe because the input string is guaranteed to be valid, meaning there are no unmatched closing parentheses. For all other characters, such as alphanumeric values or operators, we simply skip them and continue to the next iteration. Once the entire string has been processed, the max_depth variable will hold the result, which is the maximum nesting depth of the parentheses. To ensure our solution is robust, we need to consider a few edge cases. First, if the string S is empty, there are no parentheses, so the maximum depth is simply 0. Similarly, if the string contains no parentheses at all, like S equals ABC123, the depth is also 0. On the other hand, the algorithm can handle deeply nested parentheses, such as in the string, where it correctly tracks the depth as it increases and decreases. The key insights here are that the algorithm dynamically tracks the current depth using the current_depth variable, eliminating the need for intermediate storage like stacks. This makes the solution highly space efficient. Additionally, the algorithm runs in n time, where n is the length of the string, as each character is processed exactly once. With only two integer variables, the space complexity is 1, meaning it uses a constant amount of memory. Finally, because the input is guaranteed to be valid, we don't need to worry about mismatched parentheses, further simplifying the implementation. The algorithm is already optimized in terms of time and space complexity. It avoids redundant operations and uses minimal memory, making it highly efficient. Let's walk through an example to see how it works. Consider the input string s equals 1 plus 2 by 3 plus 8/4 plus 1. We start with current_depth equals 0 and max_depth equals 0. As we traverse the string, each increments current_depth and potentially updates max_depth. For the first, current_depth becomes 1, and max_depth is updated to 1. For the next, current_depth increases to 2, and max_depth updates to 2. For the next, current_depth becomes 3, and max_depth updates to 3. When encountering, current_depth decreases as we exit nesting levels. This process continues until the end of the string. At the conclusion, the max_depth remains 3, which is the deepest level of nesting in the string. Thus, the output is 3. The provided Python implementation solves LeetCode problem number 1614, maximum nesting depth of the parentheses, using an efficient approach. Here's a detailed step-by-step explanation. 1. Class and function setup. The solution is encapsulated within a class solution to adhere to LeetCode's required structure. The method maxDepth takes a string s as input and returns an integer representing the maximum nesting depth of parentheses. 2. Variable initialization. Max_depth is initialized to 0 and will track the highest depth encountered during the traversal of the string. Current_depth is initialized to 0 and represents the current nesting level as we process the string. 3. Iterating through the string. The function uses a for loop to examine each character in the input string s. If the character is an opening parenthesis, it signifies that we are entering a deeper level of nesting. In this case, current_depth is increment by 1. Then, max_depth is updated to the maximum of its current value and current_depth to ensure we always capture the deepest level encountered so far. If the character is a closing parenthesis, it indicates the end of the current nesting level. The current_depth is decrement by 1 to reflect this. 4. Edge case handling. The algorithm assumes that the input string s is valid, meaning every opening parenthesis has a corresponding closing parenthesis, as per the problem constraints. This ensures that current_depth will never become negative. Non-parenthesis characters, e.g., letters, digits, are ignored by the loop since they do not affect the depth. 5. Returning the result. After processing the entire string, the function returns max_depth, which contains the maximum nesting depth of parentheses encountered. This solution operates with a time complexity of n, where n is the length of the string s, as it processes each character exactly once. The space complexity is 1, because no additional data structures are used, and the depth is tracked using simple variables. The implementation is concise, efficient, and handles all valid inputs as specified in the problem constraints. This is the Java implementation for LeetCode problem number 1614, maximum nesting depth of the parentheses. The solution mirrors the Python logic, iterating through the input string, increasing the depth for each, and decreasing it for each. The maximum depth is updated dynamically. Key differences include Java's type declarations and the use of a for each loop to iterate over the string's characters. To solve this problem, we start by initializing two variables, max_depth to 0, which will track the deepest level of nesting we've encountered, and current_depth to 0, which keeps track of the current level of nesting as we traverse the string. Now, let's examine the input string s equals 1 plus 2 by 3 plus 8/4 plus 1. The first character, at index 0, signifies the start of a new level of nesting. So, we increment current_depth to 1 and update max_depth to the maximum of 0 and 1, which is 1. The next few characters, 1 and plus, don't affect the nesting level, so current_depth remains unchanged. Then, at index 3, we encounter another, meaning we enter a deeper level of nesting. Here, we increment current_depth to 2 and update max_depth to the maximum of 1 and 2, resulting in 2. At index 7, we encounter a closing parenthesis, which signifies the end of the current nesting level, so we decrement current_depth back to 1. Finally, at index 10, another opening parenthesis increases the depth again. At index 10, current_depth increases to 2 due to the opening parenthesis. Then, at index 11, another is encountered, taking us to a new maximum depth of 3. We update max_depth to the maximum of 2 and 3, which is 3. As we continue, at index 14, we encounter a closing parenthesis, reducing current_depth back to 2. The next closing parenthesis at index 15 reduces current_depth further to 1, and the final closing parenthesis at index 16 brings current_depth back to 0, meaning we have exited all levels of nesting. At the end of the traversal, the deepest nesting we encountered was 3, so the final output for this example is max_depth equals 3. Now, let's look at another example, S equals A, B, C, D, E, F. Again, we initialize max_depth to 0 and current_depth to 0. As we start iterating through the string, the first character, at index 0 increases current_depth to 1, and we update max_depth to the maximum of 0 and 1, which is 1. At index 2, another is encountered, increasing current_depth to 2. We then update max_depth to the maximum of 1 and 2, resulting in 2. Next, at index 4, we encounter yet another, which takes us to a new level of nesting. Here, current_depth becomes 3, and max_depth is updated to the maximum of 2 and 3, which is 3. Moving on, at index 5, a closing parenthesis reduces current_depth back to 2, while max_depth remains unchanged because it only tracks the deepest level encountered. Continuing with the same example, at index 7, another closing parenthesis reduces current_depth to 1, and at index 9, the final closing parenthesis brings current_depth back to 0, meaning all nesting has been closed. At the end of this traversal, the deepest level of nesting was 3, so the final output is max_depth equals 3. Now, let's move to a simpler example where the input string is S equals. As before, we start by initializing max_depth to 0 and current_depth to 0. Then, we begin iterating through the string. In this example, the first character, at index 0 increases current_depth to 1, and we update max_depth to the maximum of 0 and 1, which is 1. The next character, at index 1 further increases current_depth to 2. We then update max_depth to the maximum of 1 and 2, resulting in 2. At index 2, another takes us to a new level of nesting, with current_depth reaching 3. Here, we update max_depth to the maximum of 2 and 3, which is 3. As we proceed, the closing parenthesis at index 3 reduces current_depth to 2, followed by another at index 4, which reduces current_depth to 1. Finally, the last closing parenthesis at index 5 brings current_depth back to 0. The traversal is complete, and the maximum depth of nesting encountered in this example is 3. Thus, the final output is max_depth equals 3. The time complexity of the solution is O(n), where n is the length of the input string. This is because the algorithm processes each character in the string exactly once using a single for loop. For each character, the operations performed are constant time. Checking whether a character is an opening or closing parenthesis is a simple if or elif condition, which is O(1). Incrementing or decrementing the current depth is a basic arithmetic operation, also O(1). Updating the maximum depth using the max function involves comparing two integers, which is again O(1). Since all these operations are constant for each character, the total time complexity scales linearly with the length of the string. Whether the input contains no parentheses, a mix of parentheses and other characters, or only parentheses, the loop always processes every character, making the time complexity consistently O(n). The space complexity of the solution is O(1), meaning it requires a constant amount of memory regardless of the input size. This is achieved because the algorithm uses only two integer variables, current_depth and max_depth, to track the nesting depth of parentheses. These variables occupy a fixed amount of space, irrespective of the length of the input string. Additionally, no extra data structures like stacks or arrays are used, which helps maintain this constant space usage. The input string itself is passed as an argument and is neither copied nor modified, so it does not contribute to the space complexity. Whether the input string is empty, contains a mix of characters, or consists entirely of deeply nested parentheses, the memory usage remains constant, making the space complexity O(1). A common alternative to this solution involves using a stack to explicitly track the nesting depth of parentheses. In such an approach, you would push an open parenthesis onto the stack for every opening bracket encountered and pop the stack for every closing bracket. The maximum size of the stack during this process would represent the maximum nesting depth. While this stack-based method also has a time complexity of O(n), as it processes each character once, its space complexity can grow to O(n) in the worst case. This happens when the input contains deeply nested parentheses, as the stack will grow in size proportional to the nesting depth. In contrast, the current solution is more efficient in space usage, as it avoids the overhead of maintaining a stack. By using only two variables, it achieves the same result with constant memory usage, O(1), while maintaining the same O(n) time complexity. To mathematically prove the time complexity, let n represent the length of the input string. The for loop iterates through all n characters, which contributes O(n) time. Inside the loop, each operation, such as checking conditions, updating variables, or comparing values, is constant time, O(1). When we multiply the O(n) iterations by the O(1) operations per iteration, the total time complexity becomes O(n). For space complexity, only two integer variables are used throughout the algorithm. These variables require a fixed amount of memory, regardless of the input size, and no additional data structures are employed. Therefore, the space complexity is O(1). This demonstrates that the solution is optimal, achieving O(n) time complexity and O(1) space complexity for this problem. Here, we're looking at some common mistakes to avoid when solving this problem. A frequent error is incorrectly counting non-parenthesis characters, such as digits or operators, in your depth calculations. This is incorrect because only the actual parentheses and influence the nesting depth. To fix this, focus solely on incrementing depth when encountering, and decrementing it for. Another mistake is failing to properly reset the depth on closing parentheses. When you see the depth must decrease by 1. If you skip this, the count will be inflated. Similarly, allowing the depth to go negative is a clear sign of unmatched closing parentheses, which is invalid. To prevent this, ensure the depth starts at 0 and remains non-negative throughout. Validating the input string beforehand helps catch these issues early. Now, let's look at two more pitfalls. One is overcomplicating the solution by using a stack to track depth. While a stack can technically work, it adds unnecessary space complexity. A simple integer counter for the current depth, along with another to track the maximum depth, is much more efficient. Another mistake is ignoring edge cases, such as an empty string or strings without any parentheses. These scenarios can lead to incorrect results or runtime errors if not handled explicitly. To avoid this, test these edge cases and ensure the output is correct, such as returning a depth of 0 for an empty string or 1 without any parentheses. Let's shift focus to what this problem emphasizes in an interview setting. The core skill being tested is your ability to maintain a running count of open parentheses and identify the maximum depth reached. It showcases how simple counters can replace more complex data structures like stacks. Clarity in handling nested structures is key, and interviewers often look for clean, efficient solutions that also account for edge cases. Be prepared to discuss why a stack isn't necessary here and how your O(n) time complexity with O(1) space is optimal. Additionally, mastering this problem helps lay the groundwork for tackling other challenges involving nested structures, tree depths, or recursive parsing. This problem is closely related to several others that you might encounter. For example, valid parentheses on LeetCode number 20 requires checking if a string of parentheses is valid, which does necessitate using a stack. Another problem, check if string is valid parentheses string, number 678, introduces wildcard characters, increasing the complexity. Remove invalid parentheses, number 301, focuses on modifying the string to balance the parentheses, while longest valid parentheses, number 32, combines validation with calculating the length of valid subsequences. Tackling these related problems can further solidify your understanding of parentheses-based challenges. Finally, let's explore some alternative approaches. One option is using a stack, which explicitly tracks depth. While this can be helpful for problems requiring additional information about matching parentheses, it increases space complexity to O(n). Another method is the two-pointer approach, which is less intuitive for this problem but very efficient for detecting balanced strings. This method is better suited to variations like finding the longest valid parentheses substring. Lastly, there's recursive parsing, which can be elegant but introduces performance overhead and risks stack overflow with deeply nested inputs. While rarely optimal, recursion can be useful for parsing more complex expressions. Great work! To summarize, we solved the problem by using an iterative approach to track the depth of nested parentheses. Remember to practice similar problems to strengthen your understanding of these concepts. Thank you for tuning in, and don't forget to like and subscribe for more solutions and tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!